Hello there, and welcome to this gentle journey through the cosmos. I'm so glad you found your way here tonight. Maybe you've had a long day filled with deadlines and decisions, or perhaps you're simply someone who finds peace in the vast mysteries that surround our small blue planet. Either way, you're exactly where you need to be. Tonight we're embarking on something special. We're going to explore 100 fascinating facts about space and time, but not in the way you might expect. These aren't the jarring discoveries that keep you awake at night wondering about your place in the universe. Instead, these are the gentle truths, the soothing revelations that remind us how beautifully interconnected everything truly is. Picture yourself floating weightlessly through the cosmos, drifting past ancient light that has traveled billions of years just to reach your eyes. Imagine the quiet dance of planets in their orbits, the soft whisper of solar winds, and the patient rhythm of pulsars marking time across the galaxy. These are the stories we'll share together as your mind begins to settle and your thoughts grow quiet. Some of what you'll hear tonight might surprise you with its elegance. Other facts will feel like gentle confirmations of things you've always sensed but never quite understood. And if these peaceful explorations help you unwind after a difficult day, or if they spark that wonderful sense of cosmic wonder that makes you feel both infinitely small and perfectly connected to everything, consider liking this video and perhaps subscribing for more journeys like this one. It helps others find their way to this quiet corner of the universe too. But for now, let your breathing slow, let your shoulders relax, and allow yourself to drift alongside me through these cosmic waters. We have nowhere urgent to be, nothing pressing to accomplish. Just you, me, and the infinite gentle mysteries of space and time. Time moves slightly slower at your feet than at your head. Einstein's theory of relativity reveals something extraordinary about the passage of time. Gravity doesn't just pull objects toward Earth, it actually warps the flow of time itself. Because your feet are marginally closer to Earth's center than your head, they experience slightly stronger gravity, and therefore time passes just a fraction slower down there. The difference is incredibly tiny, measured in nanoseconds over a lifetime, but it's real and measurable with precise atomic clocks. This gentle stretching of time happens everywhere mass exists, creating an invisible symphony of temporal variations flowing through the universe like a quiet tide. The universe is expanding, but not into anything. When we say space is expanding, it's natural to wonder what it's expanding into. But the universe isn't growing into some larger container. Instead, space itself is stretching, carrying galaxies along like dots on an inflating balloon. There's no edge to cross, no boundary to breach. The fabric of reality is simply becoming more spacious, creating room for new possibilities while preserving the delicate relationships between all things. This expansion happens so gradually that you'd never notice it in your daily life, yet it's the grand choreography that shapes our cosmic future. Every atom in your body was forged in the heart of a dying star. Long before Earth existed, massive stars lived brilliant lives, fusing simple hydrogen into increasingly complex elements. When these stellar giants reached the end of their journeys, they scattered their treasures across space through spectacular explosions. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were born in these ancient stellar furnaces. You are quite literally made of star stuff, carrying within you the legacy of cosmic processes that unfolded over billions of years. In this way, you're not separate from the universe. You're a beautiful expression of it. Light from the sun takes 8 minutes to reach Earth, but up to 100,000 years to escape from the sun's core. When you feel sunshine warming your face, you're experiencing photons that began their journey at the sun's surface just 8 minutes ago. But those same photons started their existence deep within the solar core perhaps 100,000 years earlier. In the sun's dense interior, light particles bounce endlessly between atoms, taking a random walk that them outward. This patient, slowly carries journey from core to surface is like a cosmic meditation, each photon gradually finding its way to freedom and ultimately to you. The cosmic microwave background radiation fills every cubic inch of space with ancient light. Surrounding us at every moment is the faint afterglow of creation itself. This cosmic microwave background is light that was released when the universe first became transparent, about 380,000 years after the Big Bang. Originally blazing hot, this radiation has been stretched and cooled by billions of years of cosmic expansion until it now appears as gentle microwaves. It's the universe's baby picture, still detectable today as a whisper of those first moments when darkness gave to light. Their way are more possible games of chess than there are atoms in the observable universe. The game of chess, with its simple rules and 64 squares, contains more possible unique games than there are atoms in all the stars and planets we can see. This number, known as the Shannon number, exceeds 10 to the power of 120. It's a beautiful reminder that complexity and infinity can emerge from elegant simplicity. Like the universe itself, chess shows us how a few fundamental principles can give rise to endless, unpredictable beauty. Neutron stars are so dense that a teaspoon of their material would weigh about 6 billion tons. These collapsed stellar cores are among the most extreme objects in the universe, packing more mass than our Sun into a sphere just 12 miles across. The matter is so compressed that protons and electrons are squeezed together into neutrons, creating a substance denser than an atomic nucleus. Despite their incredible density, neutron stars spin with remarkable precision, some rotating hundreds of times per second like cosmic lighthouses sweeping their beams across space with clockwork regularity. The Milky Way and Andromeda galaxies are slowly approaching each other at 250,000 miles per hour. In about 4.5 billion years, these two massive spiral galaxies will merge in a cosmic dance that will reshape both systems. But don't worry, the collision will be more like a graceful waltz than a violent crash. The vast spaces between stars mean that very few stellar collisions will occur. Instead, gravitational forces will weave the two galaxies together, creating new formations stellar and eventually forming a single, larger elliptical galaxy that astronomers have already nicknamed Milkomeda. Venus rotates so slowly that a day there is longer than a year. While Venus takes 243 Earth days to complete one rotation on its axis, it only takes 225 Earth days to orbit the Sun. This means that if you lived on Venus, you would experience fewer than 2 sunrises per year. The planet also rotates backwards compared to most other planets, possibly due to a massive collision early in its history. This leisurely rotation creates extreme temperature differences and contributes to Venus's thick, crushing atmosphere. The Great Wall of China is not visible from space with the naked eye, but city lights are beautifully visible at night. Contrary to popular belief, the Great Wall is too narrow to see clearly from orbit without magnification. However, the warm glow of human civilization is easily visible from space after dark. Astronauts describe how cities appear as glowing webs of light spreading across the continents, creating patterns that reveal how humanity has settled and connected across the planet. These lights represent millions of lives, dreams and stories, all twinkling together in the cosmic darkness. Time dilation means astronauts on the International Space Station age slightly slower than people on Earth due to their high orbital velocity and reduced gravitational field. Astronauts experience time slightly differently than we do on the surface. The effect is tiny, just a few milliseconds per year, but it's measurable and real. After spending a year in space, an astronaut returns having aged about 5 milliseconds less than their Earthbound counterparts. It's a gentle reminder that time is not the fixed river we imagine, but rather a flowing stream that bends and curves with motion and gravity. Jupiter acts as a cosmic vacuum cleaner, protecting inner planets from asteroids and comets. This massive gas giant with its powerful gravitational field captures or deflects many potentially dangerous objects that might otherwise threaten Earth and the other inner planets. Jupiter's gravitational influence has been shaping our solar system for billions of years, clearing debris and creating relatively safe zones where life can flourish. In this way, Jupiter serves as a gentle guardian, quietly protecting the smaller worlds that orbit closer to the Sun. The Oort cloud, a spherical shell of icy objects, surrounds our solar system at distances up to 100,000 times farther from the Sun than Earth. This vast, diffuse collection of comets and ice balls forms the outermost boundary of our solar system's gravitational influence. Most of these objects are too small and distant to see, existing in a perpetual twilight where the Sun appears as just another bright star. The Oort cloud represents the solar system's quiet frontier, a peaceful realm where time moves differently and the influence of our Sun gradually fades into the interstellar medium. Saturn's moon. Titan has liquid methane lakes and rivers, creating an alien version of Earth's water cycle. On this fascinating world, methane plays the role that water plays on Earth. Clouds of methane form in Titan's thick atmosphere, creating methane rain that fills lakes and carves river channels through the landscape. The temperatures are so cold that methane exists as a liquid, while water ice is as hard as rock. This creates a dreamlike landscape where familiar processes unfold in entirely alien materials, reminding us of the infinite creativity of natural systems. The speed of light is not just a cosmic speed limit, it's also the speed of causality itself. Nothing can travel faster than light because light speed represents the fundamental rate at which cause and effect can propagate through the universe. When something happens here, the information about that event spreads outward at light speed, creating an expanding sphere of influence. This cosmic speed limit ensures that the universe remains coherent and comprehensible, preventing paradoxes and maintaining the orderly flow of time from past to future. Dark matter makes up about 85% of all matter in the universe, yet we can't see or directly detect it. This invisible substance reveals itself only through its gravitational effects on visible matter and light. Dark matter provides the scaffolding upon which galaxies form and evolve, creating the large-scale structure of the universe. Despite being all around us, passing through our bodies every second, dark matter interacts so weakly with ordinary matter that we barely notice its presence. It's a reminder that the universe holds many gentle mysteries, invisible forces that shape reality from behind the scenes. The Voyager spacecraft are now in interstellar space, carrying golden records with sounds and images from Earth. Launched in 1977, these robotic ambassadors have traveled farther from Earth than any human-made objects. Each carries a golden phonograph record containing music, natural sounds, and greetings from Earth in 55 languages. These records are designed to last billions of years, serving as a message in a bottle cast into the cosmic ocean. The Voyagers continue their journey into the unknown, carrying with them the hopes and dreams of humanity. Binary stars often orbit so closely that they share material in a cosmic dance of mutual influence. Many stars exist in pairs, locked in gravitational embraces that can last billions of years. In some systems, the stars are so close that material flows from one to the other, creating spectacular displays of cosmic partnership. These stellar couples remind us that even in the vast loneliness of space, companionship and connection are common, with stars sharing their very essence across the emptiness between them. The cosmic web connects galaxies across billions of light years through filaments of dark matter and gas. On the largest scales, the universe resembles a vast web, with galaxies strung along invisible threads like dewdrops on a spider's web. These cosmic filaments channel matter and energy across unimaginable distances, creating the backbone upon which all cosmic structure hangs. Between the filaments lie vast voids, nearly empty regions where very little matter exists, creating a of connection, cosmic architecture, and emptiness that spans the universe. The observable black holes are not cosmic vacuum cleaners that devour everything around them. Contrary to popular imagination, black holes don't actively suck in surrounding matter like some celestial drain. They simply exist as regions where gravity has become so intense that nothing, not even light, can escape once it crosses the event horizon. But at safe distances, their gravitational pull is no stronger than that of any other object with equivalent mass. If our Sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting normally, though we'd certainly miss the warmth and light. Black holes are patient entities, growing slowly and steadily through the gentle accumulation of matter that ventures too close. The sound of space is not silence, but rather a symphony we cannot hear. While sound waves cannot travel through the vacuum of space, the cosmos is filled with electromagnetic radiation that can be converted into audio frequencies. The haunting songs of Jupiter's magnetosphere, the rhythmic pulses of pulsars, and the crackling whispers of solar wind all create a hidden soundtrack to the universe. Radio telescopes capture these cosmic melodies, translating the electromagnetic poetry of space into sounds that would make any composer weep with wonder. In this way, space sings constantly. We simply need the right instruments to hear its celestial music. Pluto's orbit is so elliptical that sometimes Neptune is actually the farthest planet from the Sun. Between 1979 and 1999, Pluto's highly eccentric path brought it closer to the Sun than Neptune, making the ice giant temporarily the most distant planet in our solar system. This cosmic game of musical chairs occurs because Pluto's orbit is tilted and stretched compared to the neat, circular paths of the other planets. Even though Pluto has been reclassified as a dwarf planet, it continues its patient journey through the outer solar system, taking 248 Earth years to complete a single orbit around our star. The temperature in space depends entirely on where you are and what's around you. In the shadow of Earth, where the International Space Station sometimes travels, temperatures can plummet to -250 degrees Fahrenheit. But in direct sunlight, the same surface can heat up to 250 degrees Fahrenheit. Without an atmosphere to distribute heat evenly, space is a realm of dramatic temperature contrasts. Near stars, space can be incredibly hot, while in the vast voids between galaxies, temperatures approach absolute zero. These extreme variations create a cosmic landscape of thermal poetry, where hot and cold dance together across the infinite stage of space. Mars has the largest volcano in the solar system, but it's been dormant for millions of years. Olympus Mons rises 13.6 miles above the surrounding plains, nearly 3 times taller than Mount Everest. This massive shield volcano was built over millions of years by countless gentle lava flows, each layer adding to its impressive height. The volcano's base is roughly the size of Arizona, yet its slopes are so gradual that if you were standing on them, you might not even realize you were on a mountainside. Olympus Mons represents the patient power of geological processes, showing us how time and persistence can create monuments that dwarf anything on Earth. Gamma-ray bursts are the brightest explosions in the universe, releasing more energy in seconds than our Sun will produce in its entire lifetime. These cosmic lighthouses occur when massive stars collapse into black holes or when neutron stars collide, creating beams of intense radiation that can be detected across billions of light years. Despite their incredible violence, gamma-ray bursts are so distant that they appear to us as brief, gentle flickers in our instruments. They remind us that the universe contains events of unimaginable power, yet from our comfortable distance, they become merely beautiful data points in humanity's ongoing conversation with the cosmos. The Goldilocks zone around our Sun is not a fixed ring, but a dynamic region that has shifted over time. This habitable zone, where liquid water can exist on a planet's surface, has moved outward as our Sun has gradually brightened over its 4.6 billion-year lifetime. Early in Earth's history, our planet was closer to the inner edge of this zone, receiving less warmth from a dimmer sun. As our star has matured and increased its energy output, the habitable zone has expanded, keeping Earth in that perfect sweet spot where oceans can exist and life can flourish. This cosmic choreography shows how stability often emerges from gradual change. Comets are time capsules from the early solar system, preserving materials that are 4.6 billion years old. These dirty snowballs spend most of their lives in the cold outer reaches of the solar system, where they remain virtually unchanged since their formation. When a comet's elliptical orbit brings it close to the Sun, solar radiation begins to vaporize its ices, creating the beautiful tail that streams behind it. Each comet carries within its frozen heart the original ingredients from which our solar system formed, making them invaluable libraries of ancient history, sailing through space on predictable schedules. The magnetic field of Earth acts like an invisible shield, protecting us from harmful solar radiation. This protective bubble, generated by the motion of molten iron in our planet's core, extends far out into space, deflecting charged particles from the solar wind. When these particles do penetrate our magnetosphere near the poles, they create the aurora borealis and aurora australis, painting the night sky with curtains of green, blue, and red light. These dancing lights are visible reminders of our planet's magnetic embrace, a gentle demonstration of the invisible forces that make life on Earth possible. Tidal forces from the Moon are gradually slowing Earth's rotation, making our days longer. Billions of years ago, an Earth day was only about 18 hours long. The gravitational dance between Earth and Moon creates tidal friction that transfers rotational energy from our planet to the Moon's orbit. As Earth slows down, the Moon slowly spirals away from us at about 1.5 inches per year. This process will continue for billions of years, eventually leading to a future where Earth and Moon are tidally locked, always showing the same face to each other like a cosmic marriage where partners gaze eternally into each other's eyes. The asteroid belt between Mars and Jupiter is not the dense, dangerous field often portrayed in movies. In reality, the asteroids are spread across such a vast volume of space that you could fly a spacecraft through the belt with virtually no chance of collision. The total mass of all asteroids combined is less than that of Earth's Moon, distributed across a region millions of miles wide. These rocky remnants from the solar system's formation drift quietly in their orbits, occasionally nudged by Jupiter's gravity into new paths. They represent the building blocks that never quite came together to form a planet, forever suspended in their ancient dance around the Sun. Pulsars are among the most precise timekeepers in the universe, more accurate than atomic clocks. These rapidly spinning neutron stars emit beams of radiation that sweep across space like lighthouse beams, creating pulses of radio waves that arrive at Earth with incredible regularity. Some pulsars are so stable that astronomers use them as cosmic chronometers to test Einstein's theories and detect gravitational waves. The most precise pulsar known keeps time to within 1 second over millions of years. These stellar remnants show us that even in death, stars can continue to serve the universe as perfect metronomes, marking time across the galaxy with unwavering dedication. The surface of Venus is hot enough to melt lead, with temperatures reaching 900 degrees Fahrenheit. This extreme heat is not due to Venus being closer to the Sun, but rather to an extreme greenhouse effect caused by its thick carbon dioxide atmosphere. The atmospheric pressure on Venus is 90 times greater than Earth's, equivalent to being 3,000 feet underwater. Despite these harsh conditions, Venus rotates so slowly and smoothly that winds in its upper atmosphere circle the planet in just 4 days, creating a dynamic system of circulation that has fascinated scientists for decades. Venus reminds us that planetary climates can evolve in dramatically different directions from similar starting points. Red giant stars represent the gentle twilight years of stellar evolution. When a star like our Sun exhausts the hydrogen fuel, in its core it begins fusing helium and expands to enormous proportions, becoming a red giant. During this phase, the star's outer layers cool and redden while its surface extends far beyond its original boundaries. If our Sun were to become a red giant today, its surface would reach beyond the orbit of Mars. These evolved stars pulp, slowly and steadily shedding their outer layers into space in beautiful nebular displays. Red giants show us that even stellar death can be a gradual, majestic process rather than a violent explosion. The rings of Saturn are made of countless ice particles, some as small as dust grains and others as large as houses. These particles orbit Saturn in a flat disk that's incredibly thin relative to its diameter, like a sheet of paper compared to a football field. The rings are constantly changing as particles collide, break apart, and clump together in an ongoing dance of creation and destruction. Shepherd moons help maintain the ring structure, using their gravity to keep particles in line and create the distinct gaps we observe. The rings of Saturn demonstrate how gravity can organize matter into patterns of breathtaking beauty and mathematical precision. Human space exploration has taken us only as far as the Moon, yet our robotic ambassadors have visited every planet in the solar system. The Voyager, Cassini, New Horizons, and dozens of other spacecraft have become our eyes and ears in the cosmos, transmitting data across millions of miles to expand our understanding of distant worlds. These mechanical explorers can travel for decades, surviving radiation, extreme temperatures, and the vast loneliness of space. They represent humanity's curiosity made manifest, carrying our questions to places where human bodies cannot yet venture and bringing back answers that reshape our understanding of our cosmic neighborhood. The Great Red Spot on Jupiter is a storm that has been raging for at least 400 years. This massive anticyclonic tempest is larger than Earth and spins counterclockwise with winds reaching 400 miles per hour. Despite its violence, the Great Red Spot appears to be gradually shrinking, having decreased in size by about half since the 1800s. The storm's longevity is maintained by Jupiter's internal heat and the planet's rapid rotation, which creates the conditions necessary for such persistent weather patterns. This ancient storm serves as a reminder that some cosmic phenomena operate on timescales that dwarf human civilization, maintaining their identity across centuries while slowly evolving. Gravitational waves ripple through space-time at the speed of light, carrying information about the most violent events in the universe. When massive objects like black holes or neutron stars spiral into each other, they create ripples in the fabric of space-time itself. These waves compress and stretch space as they pass, but the effect is so tiny that it took decades to develop instruments sensitive enough to detect them. The first direct detection of gravitational waves in 2015 opened an entirely new window into the cosmos, allowing us to hear cosmic events that produce no light. These space-time ripples represent Einstein's theory of relativity made manifest, showing us that space and time are not fixed, but dynamic and responsive to matter and energy. Alpha Centauri, our nearest stellar neighbor, is actually a system of 3 stars locked in a gravitational dance. Located just over 4 light-years away, this triple star system consists of Alpha Centauri A and B, which orbit each other closely, and Proxima Centauri, a small red dwarf that orbits the pair at a much greater distance. Proxima Centauri hosts at least one potentially habitable planet, making it the closest known exoplanet to Earth. If we could travel at the speed of light, it would still take over 4 years to reach this nearest stellar neighbor, emphasizing the vast scales involved in interstellar travel. The Alpha Centauri system reminds us that even our closest cosmic neighbors exist at distances that challenge our imagination. The concept of absolute zero represents the theoretical temperature at which all molecular motion ceases, At minus 459.67 degrees Fahrenheit, particles would have minimal energy, and movement would essentially stop. While this temperature has never been achieved in nature or laboratories, scientists have come incredibly close, reaching temperatures just billionths of a degree above absolute zero. At these extreme temperatures, matter behaves in strange and wonderful ways, with gases becoming superfluids and metals becoming superconductors. The quest to reach absolute zero has led to discoveries that revolutionized our understanding of physics and opened doors to technologies we're still learning to harness. Supermassive black holes lurk at the centers of most galaxies, including our own Milky Way. The black hole at the center of our galaxy, known as Sagittarius AI, contains the mass of about 4 million suns, compressed into a region smaller than our solar system. Despite its immense gravitational pull, this cosmic giant is currently quiet, accreting matter slowly and steadily. These central black holes grow alongside their host galaxies in a delicate balance, their gravity helping to regulate star formation and the flow of gas throughout the galactic disk. They represent the hidden architects of galactic evolution, shaping the cosmic structures we see today through their patient gravitational influence. Exoplanets exist in stunning variety, from worlds of diamond and glass to planets where it rains molten metal. Among the thousands of planets discovered beyond our solar system, some challenge our understanding of what worlds can be. There are planets made primarily of carbon that may have diamond cores, worlds where the atmosphere is so thick that the surface pressure would crush any spacecraft we could build. Some exoplanets orbit their stars so closely that their surfaces are molten rock, while others drift in eternal darkness, frozen solid in the space between stars. These alien worlds remind us that nature's creativity knows no bounds, crafting environments we could never have imagined from the comfort of our temperate, water-covered home. The solar wind carries charged particles from the sun at speeds of over 1 million miles per hour. This invisible river of plasma flows constantly outward from our star, creating a bubble of solar influence that extends far beyond the orbit of Pluto. When this stream of particles encounters planetary magnetic fields, it can create spectacular light shows like the aurora on Earth, or gradually strip away atmospheres as it has done to Mars over billions of years. The solar wind shapes the tails of comets, always pointing them away from the sun, regardless of the direction of their motion. This gentle but persistent force demonstrates how even stars breathe, exhaling part of themselves into the cosmic ocean. Brown dwarfs are failed stars that never quite achieved the mass needed to sustain nuclear fusion. These cosmic in-betweens are too large to be planets but too small to be true stars, glowing dimly with the leftover heat from their formation. They drift through space like stellar ghosts, slowly cooling over billions of years until they fade into darkness. Some brown dwarfs have their own planetary systems, creating miniature solar systems where the central object barely glows warmer than a campfire. These failed stars remind us that the universe is filled with objects that don't fit neatly into our categories, existing in the quiet spaces between our definitions. The galactic year represents the time it takes our solar system to complete one orbit around the center of the Milky Way. This cosmic year lasts approximately 225 to 250 million Earth years, meaning our planet has experienced only about 18 to 20 galactic years since life first appeared. During our most recent galactic year, dinosaurs emerged, flourished, and went extinct. Continents drifted across the planet's surface, and complex life evolved from simple cellular organisms. The concept of the galactic year provides a humbling perspective on time, showing us that even our planet's entire biological history represents just a handful of trips around our galactic home. Quasars are among the most luminous objects in the universe, powered by supermassive black holes consuming matter at incredible rates. These cosmic beacons can outshine entire galaxies, making them visible across billions of light years. The light we see from distant quasars began its journey when the universe was young, offering us glimpses into cosmic adolescence. As matter spirals into the central black hole, it heats up and glows with intense radiation, creating jets of particles that stream outward at nearly the speed of light. Quasars represent cosmic engines of unimaginable power, yet from our distant perspective, they appear as gentle points of light in our most sensitive telescopes. The Kuiper belt extends beyond Neptune's orbit, populated by icy remnants from the solar system's formation. This donut-shaped region contains thousands of objects, including Pluto, Eris, and many smaller bodies that never coalesced into full planets. These frozen worlds preserve pristine samples of the materials from which our solar system formed, existing in a perpetual deep freeze where the sun appears as merely a bright star. Occasionally, gravitational perturbations send Kuiper belt objects on long journeys toward the inner solar system, where they become the spectacular comets that our skies. The Kuiper grace belt represents Solar, our system's attic, storing ancient treasures from the era of planetary formation. Stellar nurseries are vast clouds of gas and dust where new stars are constantly being born. These nebulae can span hundreds of light years and contain enough material to create thousands of stars. Within these cosmic wombs, gravity slowly pulls material together until the density and temperature become high enough to ignite nuclear fusion. The process is remarkably inefficient, with only about 1% of the cloud's material actually forming stars, while the rest is blown away by stellar winds and radiation. Each star formation event is like a cosmic birth announcement, lighting up the surrounding nebula and revealing the intricate structures carved by stellar winds and radiation pressure. The Chandrasekhar limit defines the maximum mass a white dwarf star can have before it undergoes catastrophic collapse. Named after the brilliant astrophysicist Subrahmanyan Chandrasekhar, this limit is approximately 1.4 times the mass of our Sun. When a white dwarf exceeds this threshold, usually by accreting material from a companion star, it triggers a Type Ia supernova explosion that can briefly outshine an entire galaxy. These stellar explosions are so consistent in their brightness that astronomers use them as standard candles to measure distances across the universe. The Chandrasekhar limit represents of nature's fundamental boundaries, a cosmic line that cannot be crossed without dramatic consequences. Magnetospheres create protective bubbles around planets with magnetic fields, shielding them from harmful cosmic radiation. Earth's magnetosphere deflects most of the solar wind, but Jupiter's is truly massive, extending millions of miles into space and trapping high-energy particles in radiation belts. These magnetic cocoons can protect planetary atmospheres from being stripped away by stellar winds, making them crucial for maintaining the conditions necessary for life. The interaction between magnetic fields and charged particles creates some of the most beautiful phenomena in the solar system, from Earth's aurora to the radio emissions from Jupiter's magnetosphere that can be detected from Earth. Rogue planets drift through interstellar space without orbiting any star, wandering the galaxy in eternal darkness. These planetary orphans may have been ejected from their birth systems through gravitational interactions, or they might have formed independently in the depths of space. Without a star's warmth, rogue planets are frozen worlds where any atmosphere has long since condensed into ice on their surfaces. Some scientists estimate there could be billions of these wandering worlds in our galaxy alone, invisible nomads carrying the stories of their lost solar systems. Rogue planets remind us that not all worlds enjoy the steady embrace of a parent star. The cosmic distance ladder is the ingenious method astronomers use to measure vast distances across the universe. Starting with nearby objects whose distances can be measured directly through parallax, astronomers use increasingly distant standard candles like Cepheid variable stars and Type Ia supernovae to extend their reach across billions of light years. Each rung of this ladder depends on the accuracy of the previous one, creating a carefully calibrated chain of measurements that spans from our solar system to the edge of the observable universe. This cosmic measuring tape allows us to map the three-dimensional structure of the universe and understand its expansion. History solar eclipses occur due to an extraordinary cosmic coincidence that makes our moon appear almost exactly the same size as the sun in our sky. The sun is about 400 times larger than the moon, but it's also about 400 times farther away, creating this perfect illusion of equal size. This remarkable alignment allows the moon to completely block the sun's bright disk during a total solar eclipse, revealing the sun's ethereal corona. Total solar eclipses are temporary phenomena, as the moon is gradually moving away from Earth and will eventually appear too small to create total eclipses. Future generations will witness only partial eclipses, making our current era special in Earth's long history. The heliopause marks the boundary where the solar wind meets the interstellar medium, creating a cosmic shoreline at the edge of our solar system's influence. This region, located about 11 billion miles from the Sun, is where the steady stream of particles from our star finally encounters the thin gas and dust that fills the space between stars. The Voyager spacecraft became the first human-made objects to cross this boundary, entering true interstellar space and beginning humanity's first direct exploration of the galaxy beyond our solar system. The heliopause represents our cosmic border, the place where the sun's influence fades and the wider galaxy begins. Globular clusters are ancient cities of stars that orbit our galaxy like stellar satellites. These spherical collections contain hundreds of thousands of old stars packed into regions just a few dozen light-years across. The stars in globular clusters formed together billions of years ago when the Milky Way was young, and they've remained gravitationally bound ever since. From a planet within a globular cluster, the night sky would be filled with thousands of bright stars, creating a spectacular celestial dome. These stellar cities provide astronomers with laboratories for studying stellar evolution and the early history of our galaxy. Planetary rings are more common than once thought, with all 4 giant planets in our solar system sporting ring systems of varying complexity. While Saturn's rings are the most spectacular and well-known, Jupiter, Uranus, and Neptune also have their own ring systems composed of dust, ice, and rocky debris. These rings form from the gravitational destruction of moons that venture too close to their parent planet, or from material that never coalesced into moons in the first place. Ring systems are dynamic structures, constantly evolving as particles collide, merge, and are influenced by the gravitational tugs of nearby moons. They represent cosmic jewelry boxes, delicate and beautiful arrangements of matter in motion. The anthropic principle suggests that the universe's physical constants seem finely tuned to allow for the existence of stars, planets, and life. If gravity was slightly stronger or weaker, if the electromagnetic force had a different strength, or if the strong nuclear force varied by small amounts, the universe would be a very different and likely lifeless place. This apparent fine-tuning has sparked debates about whether our universe is one of many, whether these constants could have been different, or whether there's some deeper principle at work. The anthropic principle reminds us that the universe we observe seems remarkably well suited for complexity in consciousness to emerge. Coronal mass ejections are massive bursts of plasma and magnetic field released from the sun's corona. These solar storms can travel at speeds of several million miles per hour, carrying billions of tons of charged particles across the solar system. When a particularly powerful coronal mass ejection reaches Earth, it can disrupt satellite communications, damage power grids, and create aurora visible at latitudes where they're normally never seen. These events remind us that our technological civilization exists within the sun's sphere of influence, and that space weather can have real effects on our daily lives. The observable universe has a finite size not because space ends somewhere, but because light has only had a finite time to reach us since the Big Bang. This cosmic horizon currently extends about 46 billion light-years in all directions, encompassing everything from which light has had time to travel to Earth. Beyond this boundary, there may be infinitely more space and matter, but it remains forever invisible to us because its light hasn't had time to make the journey. As time passes, this horizon slowly expands, gradually revealing more of the universe, like dawn slowly illuminating a vast landscape. Tidally locked planets always show the same face to their star, creating worlds of permanent day and eternal night. Many exoplanets orbiting close to their stars experience such strong tidal forces that their rotation becomes synchronized with their orbital period. This creates planets where one hemisphere bakes in constant starlight, while the other freezes in perpetual darkness. Between these extremes lies a twilight zone where temperatures might be just right for liquid water to exist. These worlds challenge our Earth-centric view of habitability, suggesting that life might find ways to thrive even in such extreme and alien environments. Vacuum decay represents a theoretical scenario where the very fabric of space could undergo a catastrophic phase transition. If the Higgs field that permeates all of space is not in its lowest possible energy state, it could theoretically tunnel to a lower state, creating a bubble of true vacuum that expands at the speed of light. This bubble would rewrite the laws of physics as it passed, fundamentally altering the nature of matter and energy. While this scenario is highly speculative and maybe impossible, it represents the ultimate example of how even empty space might not be as stable as it appears. The multiverse hypothesis suggests that our universe might be just one of countless others, each with potentially different physical laws and constants. Some versions of this idea arise from eternal inflation theory, which proposes that the rapid expansion following the Big Bang continues in other regions of space, constantly creating new universe bubbles. Other versions emerge from quantum mechanics, suggesting that every quantum measurement creates branching realities. While the multiverse remains highly theoretical and may be forever untestable, it offers a humbling perspective on our cosmic significance, suggesting that even our entire observable universe might be just one small part of an infinitely larger reality. And so, our gentle journey through the cosmos continues, each fact a soft stepping stone across the infinite ocean of space and time. These truths float around you now like stardust, some settling into memory, while others drift away into the peaceful darkness of approaching sleep. The universe unfolds its secrets not with urgency or demand, but with the patient rhythm of celestial bodies moving through their ancient dances, carrying you along on waves of cosmic wonder toward whatever dreams await in the quiet spaces between stars. Wormholes, if they exist, would create shortcuts through the fabric of space-time itself. These theoretical tunnels could potentially connect distant regions of the universe, or even different universes entirely, allowing for instantaneous travel across vast cosmic distances. Einstein and his colleague Nathan Rosen first proposed these bridges in 1935, though they remain purely theoretical. The challenge with wormholes is keeping them stable and open long enough for anything to pass through. Most theoretical models suggest they would collapse almost instantly, unless exotic matter with negative energy density could prop them open. While wormholes capture our imagination as cosmic highways, they remain one of physics' most beautiful and elusive possibilities, existing primarily in the realm of mathematical poetry. Cosmic inflation explains why the universe appears so uniform in all directions. In the first fraction of a second after the Big Bang, space itself expanded exponentially, stretching tiny quantum fluctuations to cosmic scales. This rapid inflation smoothed out any irregularities that might have existed in the early universe, creating the remarkably uniform cosmic microwave background radiation we observe today. The theory also explains why space appears to be geometrically flat on the largest scales, like a balloon being inflated so quickly that any wrinkles on its surface disappear. Cosmic inflation transformed a possibly chaotic early universe into the ordered cosmos we inhabit. The Pioneer anomaly puzzled scientists for decades, as both Pioneer 10 and 11 spacecraft experienced an unexplained deceleration. As these robotic explorers journeyed toward the outer solar system, they gradually slowed down more than expected based on known gravitational forces. For years, this anomaly sparked speculation about new physics or unknown forces at work in the outer solar system. The mystery was finally solved when scientists realized that thermal radiation from the spacecraft's own power sources was creating a tiny but measurable rocket effect, gently pushing against their forward motion. This subtle discovery reminds us that even in the vastness of space, the smallest effects can accumulate over time and distance. Lagrange points are cosmic parking spots where gravitational forces balance perfectly. These 5 special locations exist in any two-body system, such as the Earth-Moon or Earth-Sun system, where a smaller object can maintain a stable position relative to the 2 larger bodies. The James Webb Space Telescope orbits at the L2 Lagrange point, about the direction opposite million miles from Earth in the Sun, where it can maintain a constant position relative to both Earth and Sun while staying in perpetual shadow. These gravitational balance points demonstrate the elegant mathematical relationships that govern celestial mechanics, creating islands of stability in the dynamic dance of gravitational forces. The cosmic web reveals the largest structures in the universe, with galaxies strung along vast filaments of dark matter like dewdrops on an invisible spider's web. These cosmic highways channel matter and energy across hundreds of millions of light years, creating the backbone of cosmic architecture. Between these filaments lie enormous voids, vast regions of space containing very few galaxies, creating a foam-like structure on the grandest scales. This cosmic web formed gradually as dark matter clumped together under its own gravity, providing the scaffolding upon which visible matter could collect and form the galaxies we see today. Hawking. Radiation suggests that black holes aren't completely black, but emit a faint glow due to quantum effects near the event horizon. According to this theory, virtual particle pairs that constantly appear and disappear in empty space can be separated at a black hole's edge, with one particle falling in while the other escapes. This process causes the black hole to very slowly evaporate over time, with smaller black holes radiating away faster than larger ones. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely, while microscopic black holes would vanish almost instantly in brilliant flashes of energy. The zodiacal light creates a faint triangular glow visible in dark skies before dawn or after sunset. This ethereal illumination comes from sunlight reflecting off countless dust particles scattered throughout the inner solar system, remnants from comets and asteroids that have been ground down over billions of years. The dust forms a disk roughly aligned with the plane of the planets, creating this ghostly pyramid of light that rises from the horizon. Ancient astronomers called it the false dawn because it appears in the east before sunrise. In our light-polluted modern world, few people ever see this gentle reminder of the cosmic dust that surrounds us. Stellar parallax provides one of the most direct methods for measuring distances to nearby stars. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars, like holding up your finger and alternately closing each eye. This tiny angular shift, measured in fractions of an arcsecond, allows astronomers to calculate stellar distances using simple trigonometry. The nearest star, Proxima Centauri, has a parallax of just 0.77 arcseconds, equivalent to the width of a dime seen from 2 miles away. This method works only for stars within a few hundred light years, beyond which the parallax becomes too small to measure accurately. The interstellar medium fills the space between stars with a thin soup of gas, dust, and charged particles. Though nearly empty by Earth standards with densities millions of times lower than the best laboratory vacuums, this material plays a crucial role in stellar formation and galactic evolution. Shock waves from supernovae compress regions of the interstellar medium, triggering the collapse of gas clouds that eventually birth new stars. The medium also acts as a cosmic recycling system, enriched by the stellar winds and explosive deaths of stars, gradually increasing the heavy element content of the galaxy over billions of years. Solar neutrinos stream through your body by the billions every second, ghostly particles that barely interact with matter. Created in the nuclear furnace at the sun's core, these nearly massless particles travel at nearly the speed of light and pass through the entire Earth as if it were transparent. Detecting these elusive messengers requires enormous underground detectors filled with thousands of tons of special materials. Solar neutrinos provide a direct window into the sun's core, confirming that nuclear fusion is indeed powering our star and allowing scientists to study stellar interiors in ways impossible with light alone. The Milky Way's central supermassive black hole, Sagittarius A, was directly imaged for the first time in 2022. This cosmic monster, containing the mass of over 4 million suns compressed into a region smaller than Mercury's orbit, lurks at the heart of our galaxy, surrounded by a swirling accretion disk of superheated gas. Despite its immense gravitational pull, Sagittarius A is currently relatively quiet, consuming matter at a modest rate compared to the more active, supermassive black holes found in distant galaxies. The successful imaging of this black hole's shadow represents a triumph of international cooperation and technological innovation. Planetary migration can dramatically reshape solar systems as massive planets spiral inward or outward from their original formation sites. Jupiter likely migrated inward toward the Sun early in our solar system's history before reversing course and moving back outward, a journey that may have scattered many smaller bodies and influenced the formation of the terrestrial planets. This grand tack hypothesis helps explain why our solar system looks different from many of the exoplanetary systems discovered around other stars. These planetary movements occur over millions of years through gravitational interactions with the disk of gas and dust from which planets form. The local group represents our cosmic neighborhood, containing over 80 galaxies bound together by gravity across a region spanning about 10 million light-years. The Milky Way and Andromeda are the two largest members of this galactic cluster, with dozens of smaller dwarf galaxies orbiting around them like cosmic satellites. The local group itself is part of the much larger Virgo supercluster, which contains thousands of galaxies and spans over 100 million light-years. These nested structures of increasing size demonstrate how gravity organizes matter on the largest scales, creating hierarchies of cosmic communities. Atmospheric escape gradually strips away planetary atmospheres over geological time, particularly affecting smaller worlds with weaker gravitational holds. Mars likely lost much of its original atmosphere to space, transforming from a potentially warm, wet world to the cold, dry planet we see today. The process occurs when atmospheric particles gain enough energy from solar heating or stellar wind interactions to overcome a planet's gravitational pull. Earth's stronger gravity and protective magnetic field help retain our atmosphere, though we still lose some hydrogen and helium to space. Understanding atmospheric escape is crucial for assessing the long-term habitability of exoplanets. Type 2 supernovae mark the spectacular deaths of massive stars. Explosions so bright they can briefly outshine entire galaxies. When a star more than 8 times the mass of our Sun exhausts its nuclear fuel, its core collapses in less than a second, creating temperatures and pressures that forge the heaviest elements in the universe. The resulting shock wave blasts the star's outer layers into space at thousands of miles per second, creating expanding shells of hot gas that can remain visible for thousands of years. These stellar explosions disperse the heavy elements necessary for planet formation and life throughout the galaxy. The anthropic landscape suggests our universe might be one of countless others in an infinite multiverse, each with different physical constants and laws. In this scenario, we find ourselves in a universe compatible with life not because it was designed for us, but because we could only evolve in a universe where the conditions were right. Most other universes in this vast landscape might be sterile, with physics that doesn't allow stars to form or chemical complexity to emerge. While impossible to test directly, this idea provides one explanation for why our universe's physical constants seem so finely tuned for the existence of complexity and consciousness. Circumstellar disks around young stars provide the raw material for planet formation, containing dust and gas that gradually clump together under gravity. These protoplanetary disks can extend for hundreds of astronomical units from their central star, with different regions at different temperatures allowing various materials to condense. Rocky planets form in the hot inner regions where only metals and silicates remain solid, while gas giants assemble in the cooler outer regions where water ice and other volatiles freeze. The entire process takes millions of years, with the disk gradually dispersing as planets form and stellar winds sweep away remaining gas. Cosmic ray showers occur when high-energy particles from space collide with Earth's atmosphere, creating cascades of secondary particles that rain down to the surface. These cosmic messengers originate from supernovae, black holes, and other violent cosmic events, carrying energies millions of times greater than particles produced in our most powerful accelerators. When they strike the upper atmosphere, they fragment into showers of muons, electrons, and other particles that can be detected at ground level. Some cosmic rays are so energetic that scientists still debate what could possibly accelerate particles to such incredible speeds. The scale height of planetary atmospheres determines how quickly air pressure drops with altitude, creating the gradual transition from surface to space. On Earth, atmospheric pressure decreases by roughly half every 18,000 feet of altitude, creating a gentle, exponential decline that extends hundreds of miles above the surface. This scale height depends on a planet's gravity and atmospheric temperature, with smaller or colder worlds having thinner atmospheric layers. Understanding scale heights helps scientists interpret observations of exoplanetary atmospheres and design missions that must navigate these transitions. From vacuum to dense atmosphere, galactic cannibalism occurs when larger galaxies gravitationally capture and eventually merge with smaller companions. Our Milky Way has consumed numerous dwarf galaxies throughout its history, with stellar streams and disrupted remnants still visible in our galactic halo. The currently Sagittarius dwarf galaxy being torn apart by our galaxy's gravity, leaving a trail of stars stretched across the sky. These mergers don't involve direct collisions between stars due to the vast distances involved, but rather a gradual gravitational dance that can take hundreds of millions of years to complete, ultimately creating larger, more massive galaxies. Fast radio bursts are mysterious millisecond flashes of radio waves that originate from distant galaxies and release as much energy as the Sun produces in days. These enigmatic signals were first discovered in 2007, and thousands have since been detected, most appearing only once before disappearing forever. Some fast radio bursts repeat at irregular intervals, providing opportunities for detailed study. Leading theories suggest they originate from highly magnetized neutron stars or involve exotic physics near black holes. These cosmic beacons demonstrate that the universe still holds surprises, with phenomena that challenge our understanding of extreme physics. The cosmic microwave background reveals tiny temperature fluctuations that served as the seeds for all large-scale structure in the universe. These variations, just millionths of a degree in temperature, represent slight density differences in the primordial plasma that filled the early universe. Over billions of years, gravity amplified these tiny ripples, causing matter to clump together and eventually form the galaxies and galaxy clusters we observe today. The precise pattern of these fluctuations provides a baby picture of the universe and strong evidence for the Big Bang. Theory and cosmic inflation. Solar cycles repeat approximately every 11 years as the Sun's magnetic field reverses and reorganizes itself. During solar maximum, the Sun displays numerous sunspots, solar flares, and coronal mass ejections, while solar minimum brings a quieter Sun with few active regions. These cycles affect space weather around Earth, influencing aurora activity, satellite operations, and radio communications. The Maunder minimum, a period of unusually low solar activity from 1645 to 1715, coincided with particularly cold winters in Europe, suggesting that solar variability may have subtle effects on Earth's climate over long timescales. Herbig-Haro objects are glowing clouds of gas created when jets of material from newborn stars collide with the surrounding interstellar medium. These colorful nebulae mark sites of active star formation where protostars are still accreting material and ejecting high-speed jets along their rotational axes. The jets heat up and ionize the gas they encounter, creating intricate structures that evolve and change over years and decades. Herbig-Haro objects provide direct evidence of the violent birth process of stars, showing how stellar formation affects the surrounding environment and helps regulate the star formation process itself. White dwarf stars represent the final fate of stars like our Sun, dense stellar cores left behind after red giant phases end. These Earth-sized objects contain about as much mass as the Sun but compressed to incredible densities, where a sugar cube would weigh as much as a car. White dwarfs are supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too tightly together. They cool slowly over billions of years, gradually fading from white-hot to red and eventually becoming cold, dark objects called black dwarfs, though the universe isn't old enough for any black dwarfs to exist yet. The Oort cloud extends far beyond Pluto's orbit, forming a spherical shell of icy debris that surrounds our entire solar system. This vast collection of comet nuclei may contain trillions of objects, most no larger than mountains, existing in a perpetual deep freeze where the Sun appears as merely a bright star. Occasionally, gravitational perturbations from passing stars or molecular clouds send Oort cloud objects on long journeys toward the inner solar system, where they become the spectacular long-period comets that grace our skies. The cloud represents the solar system's most distant frontier, extending halfway to the nearest star. Netars possess magnetic fields trillions of times stronger than Earth's, capable of warping atoms and affecting matter hundreds of miles away. These exotic neutron stars generate their extreme magnetic fields through rapid rotation and convection in their superfluid interiors. A magnetar's field is so intense that it could erase credit cards from hundreds of miles away and would be lethal to humans at distances greater than the Moon's orbit. Occasionally, magnetars release tremendous bursts of gamma rays and X-rays, briefly becoming the brightest objects in the known universe. These events provide glimpses into physics under the most extreme conditions imaginable. The habitable zone around each star defines the orbital distance where liquid water could exist on a planetary surface, creating a cosmic Goldilocks region that's neither too hot nor too cold. This zone shifts outward for more massive, luminous stars and inward for smaller, dimmer ones. However, the habitable zone concept continues to evolve as scientists discover that planetary atmospheres, geological activity, and even tidal heating from giant planet neighbors can dramatically affect surface conditions. Moons of giant planets, like Europa and Enceladus, maintain liquid water oceans beneath their icy surfaces through tidal heating, existing well outside their star's traditional habitable zone. Stellar wind bubbles form when the charged particles streaming from stars collide with the interstellar medium, creating vast cavities in space. Our Sun's solar wind creates the heliosphere, a bubble extending well beyond Pluto that shields the inner solar system from some cosmic rays. More massive stars produce much stronger stellar winds that can carve out enormous cavities hundreds of light years across. These bubbles affect star formation in surrounding regions, sometimes triggering new stellar birth by compressing nearby gas clouds, while other times dispersing potential star-forming material. The interaction between stellar winds and interstellar space creates some of the most beautiful and complex structures visible in nebulae. Binary star systems often engage in dramatic exchanges of material, with one star gradually stealing gas from its companion in a process called mass transfer. When a white dwarf accumulates enough hydrogen from a companion star, the stolen material can ignite in a thermonuclear explosion called a nova, briefly making the system thousands of times brighter. In extreme cases, this process can push a white dwarf beyond its maximum stable mass, leading to a type Ia supernova that completely destroys the star. These stellar partnerships demonstrate that even in the apparent isolation of space, celestial objects frequently interact and influence each other's evolution in dramatic ways. And now, as we drift deeper into this cosmic meditation, let the gentle weight of these discoveries settle around you like starlight on still water. Each truth we've shared carries within it the patient work of countless scientists, the accumulated wisdom of generations who looked up at the night sky and wondered. These facts float through your consciousness now, some bright and clear, others soft and dreamlike, all part of the vast tapestry that connects you to the infinite dance of space and time surrounding us in this quiet moment of understanding. The event horizon of a black hole represents a one-way boundary. Through SPAC velocity equals the time where they escape the speed of light, this invisible sphere surrounds the black hole's singularity, marking the point of no return for anything that crosses it. Interestingly, the size of an event horizon depends only on the black hole's mass, not its density. A supermassive black hole might have an event horizon larger than our solar system, while a stellar mass black hole's boundary would span just a few miles. Time dilation near the event horizon means that to an outside observer, objects appear to slow down and fade away as they approach this cosmic threshold, never quite seeming to cross over, frozen forever at the edge of forever. Tidal heating can keep moons warm and geologically active, even in the cold outer solar system. Jupiter's moon, Io, experiences such intense tidal forces from its giant parent that its interior remains molten, creating the most volcanically active world in our solar system. Europa and Enceladus maintain liquid water oceans beneath their icy shells through similar tidal flexing, as their elliptical orbits cause their shapes to change slightly with each revolution. This gentle kneading action generates heat through friction, like repeatedly bending a paperclip until it becomes warm. These hidden oceans may harbor more water than all of Earth's surface oceans combined, representing some of the most promising locations to search for life beyond our planet. Planetary formation occurs through a process called accretion, where tiny dust grains gradually stick together to build increasingly larger objects. In the disk of material surrounding a young star, microscopic particles collide and adhere through static electricity and weak molecular forces. Over millions of years, these grow into pebbles, then rocks, then boulders, and eventually planetesimals the size of asteroids. The largest of these objects develop enough gravity to begin attracting additional material, growing faster as they sweep up debris in their orbital paths. This runaway process can create planets within just a few million years, though the final stages of planetary formation can involve violent collisions that reshape entire worlds. Red dwarf stars burn so slowly and efficiently that they can shine for trillions of years, far longer than the current age of the universe. These small, cool stars consume their hydrogen fuel at such a leisurely pace that they will outlive every other type of star by enormous margins. While our Sun will exhale in about 5 billion years, its fuel red dwarfs can continue shining for 100 billion years or more. This incredible target's longevity makes them fascinating for as their biology planetary systems have vast amounts of time for life to evolve and develop. In the far future, when all other stars have died, red dwarfs will be the last lights burning in an increasingly cold and dark universe. The solar system's architecture reflects the temperature gradient that existed in the early protoplanetary disk. Close to the young sun, only rocky materials could condense from the hot gas, leading to the formation of small, dense planets like Mercury, Venus, Earth, and Mars. Beyond the frost line, where water could freeze into ice, much more material was available for planet building, allowing the gas giants Jupiter, Saturn, Uranus, and Neptune to form. This fundamental organizing principle explains real planets cluster wide terrest near the Sun, while gas giants dominate the outer solar system. The asteroid belt marks a transitional zone where Jupiter's powerful gravity prevented the formation of a full-sized planet. Stellar nucleosynthesis creates elements heavier than hydrogen and helium in the cores of stars through nuclear fusion. As stars age, they fuse lighter elements into heavier ones, working their way up the periodic table from helium to carbon, oxygen, and beyond. The most massive stars can create elements as heavy as iron in the limits their cores before reaching of energy-producing fusion. Elements heavier than iron require the extreme conditions of supernovae or neutron star collisions to form, making them relatively rare in the universe. Every atom in your body heavier than hydrogen was created either in the core of a star or during a violent stellar explosion, connecting you directly to these cosmic furnaces. The cosmic distance scale spans an almost incomprehensible range, from subatomic particles to the observable universe itself. If an atom was scaled up to the size of a marble would need to be scaled up to the size of Earth to match the same proportional increase. Similarly, if Earth was shrunk to the size of a marble, the nearest star would still be thousands of miles away. These vast scales make space exploration incredibly challenging, as even our fastest spacecraft would take tens of thousands of years to reach the nearest star. The universe operates on scales that stretch human comprehension to its limits, requiring new ways of thinking about distance, time, and our place in the cosmic order. Galactic rotation curves reveal one of the most profound mysteries in modern astronomy. When fast stars orbit around galaxy astronomers measured how the outer region's centers, they discovered that stars in much faster than expect moved based on the visible matter alone. According laws to Newton, stars farther from our solar system move just planets in more galaxies' center should orbit more slowly, as outer yearly than lays ones. Instia interactic rotation remains, Gal roughly constant across vast distances, suggesting the presence of additional invisible mass. This discovery led to the realization that galaxies are embedded in massive halos of dark matter, fundamentally changing our understanding of cosmic structure. Gravitational time dilation affects the passage of time throughout the universe, creating a complex temporal landscape where different at different rates. CL regions experience time arcs run slightly faster on Mount sea level due to Earth tops than its weaker gravitational field at higher altitudes. This affects massive objects like black holes, where time can become extreme, near slow to a crawl relative account for both gravitational and to distant observers. GPS satellites must velocity-related time dilation to maintain accuracy, correcting for the verses on Earth's surface. This different rates at which time passes in orbit, malleability of time, revealsative, sense of universal that are into. Simultaneity is merely an approximation valid only in weak wave background polar the information about gravitational fields. Cosmic microization carries lationary epicational waves from, as the universe underwent its first moments, quantum fluctuations in space, rapid expansion in a time itself was stretched to cosmic prints in the polarization pattern scales, potentially leaving detectable IM of the cosmic microwave background. These primordial gravitational waves were inflation and provided represent direct evidence of cosmic insights into physics at energy scales far accelerators. The search beyond anything achievable in particle for these subtle requires instruments of polarization, signals extraordinary sensitivity, as the effect is buried beneath foreground contamination from our own galaxy and other sources. Stellar rem their diverse final forms. White ants tell the story of stellar evolution through endings of sun-like stars. Slowly dwarfs represent the gentle cooling over billions of years like cosmic embers. Neutron stars mark the violent collapse of more massive stars, creating objects so dense that their atoms are crushed into a soup of neutrons. Black holes form when even neutron degeneracy pressure cannot halt gravitational collapse, creating regions where space-time curves so severely that nothing history, serving as cosmic mass, composition, and evolutionary can escape. Each type of remnant preserve, fossils that reveal the process, seizes information about its progenitor stars shaping stellar populations across time. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by breaking down the problem into component of star formation, the fraction of stars factors. These include the rate with planets, the number of planets per star in habitable zones, and the likelihood of life-developing intelligence and technology. While many of these factors remain highly uncertain, the equation provides a framework for thinking about our cosmic loneliness or companionship. Even conservative estimates suggest that if life commonly develops on suitable worlds, our galaxy should host numerous technological civilizations. The apparent absence of obvious alien signals, known as the Fermi paradox, remains one of the most intriguing puzzles in astrobiology. Solar flares and coronal mass ejections demonstrate the dynamic nature of our seemingly steady sun. These explosive events release enormous amounts of energy and charged particles into space, sometimes affecting Earth's magnetic field and creating beautiful aurora displays at unusual latitudes. The largest solar storms can disrupt satellite communications, damage power grids, and pose radiation hazards to astronauts. Historical records suggest that truly Carrington event of 1859, massive solar events like that could have catastrophic effects on our modern electronic infrastructure. As our civilization becomes increasingly dependent on technology, understanding and predicting space weather becomes ever more critical for maintaining our connected world. Exomoons represent an entirely new class of potentially habitable worlds orbiting planets beyond our solar system. While we've discovered thousands of exoplanets, detecting their moons remains at the edge of current observational capabilities. Large moons orbiting gas giants in habity water through tidal heating, expanding thatable zones could maintain stable climates and liquid alone. In our number of potentially habitable worlds far beyond planets does demonstrate that own solar system. Moons like Europa and Encella different from Earth's surface, complex chemistry, and possibly life can thrive in environments very. The search for exomoons represents our solar system. Galactic Chemical, the next frontier in the hunt for life beyond evolution, traces how complex over cosmic time. The universe has become increasingly first stars formed from pure hydrogen and helium, creating heavier elements through nuclear fusion and dispersing them through stellar winds and supernova explosions. Each subsequent generation of stars inherited a slightly richer mixture of elements, enabling the formation of rocky chemistry necessary for life. This planet's and the complex gradual enrichment continues today as dying stars contribute their processed materials to the interstellar medium. On this, our existence depends 13 billion-year process of cosmic recycling, making us products of countless stellar generations. Vacuum metastability suggests that the empty space around us might not be in its lowest possible energy state. If the Higgs field exists in a false vacuum, it could theoretically tunnel to a lower energy configuration, fundamentally altering the laws of physics throughout the universe. Such a vacuum decay event would propagate outward at the speed of light, rewriting reality as it passed and making the universe uninhabitable for any existing life forms. While this scenario remains highly speculative and maybe impossible, it represents one of the most profound ways that our apparently stable reality might be more fragile than it appears. The cosmic web's filamentary structure emerged from tiny quantum fluctuations in the early universe that were amplified by gravitational instability over billions of years. Dark matter clumped first along these cosmic superhighways, providing the gravitational scaffolding for ordinary matter to follow. Gas flowed along these filaments toward the intersections where galaxy clusters formed, creating the largest gravitationally bound structures in the universe. This cosmic architecture continues to evolve today, with galaxies moving along filaments and merging at the nodes where multiple streams converge. The web-like pattern repeats across vast scales, from individual galaxy clusters to superclusters spanning hundreds of millions of light years. Planetary magnetic fields arise from dynamo processes in electrically conductive fluid layers within planetary interiors. Earth's magnetic field originates from the motion of molten iron in its outer core, driven by heat flow and the planet's rotation. This geodynamo has operated for billions of years, though it occasionally reverses polarity in a process that can take thousands of years to complete. Mars likely once possessed a global magnetic field, but lost it as its interior cooled and solidified, leading to the gradual loss of its atmosphere to space. Understanding planetary magnetism helps scientists assess the habitability of exoplanets and the long-term stability of their atmospheres. The concept of space-time as a unified, four-dimensional fabric revolutionized our understanding of gravity and the universe itself. Einstein's general relativity describes gravity not as a force between masses, but as the curvature of space-time caused by the presence of matter and energy. Massive objects create wells in this fabric, causing other objects to follow curved paths that we interpret as gravitational attraction. This geometric view of gravity explains phenomena from planetary orbits to the expansion of the universe itself. Space-time is not merely the stage upon which cosmic drama unfolds, but an active participant that can be stretched, twisted, and warped by the matter and energy it contains. Brown dwarf demographics reveal a hidden population of substellar objects that bridge the gap between the most massive planets' massive stars. These fail, and the least stars never achieved the temperatures and pressures necessary to sustain hydrogen fusion, instead cooling slowly over billions of years while glowing dimly in infrared light. Some brown dwarfs host their own planetary systems, creating miniature solar systems where the central object provides barely more warmth than a campfire. Recent surveys suggest that brown dwarfs may be nearly as common as true stars, representing a significant but largely invisible component of galactic mass. Their study helps astronomers understand the lower limits of star formation and the transition between stellar and planetary physics. And so we drift onward through these cosmic currents, each revelation a gentle wave carrying us deeper into the infinite ocean of understanding. The universe reveals its secrets not through force or haste, but through patient observation and quiet contemplation, each discovery building upon the last like sedimentary layers of knowledge accumulating over generations of wonder. These truths surround you now, some as stars, others as faint as distant bright as nearby galaxies, all part of the vast symphony of existence that plays on scales both impossibly large and intimately small, connecting every atom in your body to the grandest structures spanning billions of light years across the cosmos.